In the second part of the lecture, our aim is to better understand the variety of complete quadrics and intersection theory on it. So recall that a point on the variety of complete quadrics is this sequence of symmetric matrices. This is how we think about it. And if A1 is of rank n, that's the dimension of V, then all of these matrices are of rank n, they are invertible, and this is somehow a general point. But what happens when A1 is not of rank R? This is what we are trying to discuss. So first of all, we get a locus of those points where the rank of A1 is R. This is not closed, so let us close it. And it turns out that this is exactly what happens if we do the Rth projection. So the matrix AR, we land in the space of quadrics, and the condition is that this quadric has rank 1. So this is also the locus of A1 up to an minus 1, such that rank of AR is 1. Right? This is a closed condition because this matrices AI, they live in projective spaces, and there is also a dual point of view, namely these are those sequences where the inverse, the dual quadric to A1, so A n minus 1, and this has rank n minus R. Again, this is not a closed condition, so this one we have to close. So our variety of complete quadrics has general points where A1 is invertible, and if A1 is not invertible, then then we are in this loci SR for some R, for some, yeah. So so in particular, this loci may intersect. They intersect in a nice way, but all together with the general points, they fill out the variety. So this is a very explicit description. Notice that because of this first condition, we also know that SR is the exceptional divisor of the blow-up. Yeah, so is the exceptional divisor of the blow-up. Yes, so one of the definitions we have of the variety of complete quadrics was as the sequence of blow-ups, and at some point we will brewing up rank R matrices, and exactly then we obtain the divisor that corresponds to SR. Okay. In particular, this is irreducible of codimension 1. So this SR and this thing, it's contained in CQV, irreducible of codimension 1. And again, it's not a very easy thing, but again, as it is for complete quadrics, it's easy to describe general points. So how does a general point of SR look like? General point on SR. Yeah, so because of those closures, because of this closure and this closure, we know that the general point needs to have rank A1 equal to R and rank n minus 1 equal to n minus R. And it turns out that in this case, the point on SR is determined by these two matrices. General point on SR is determined by A1 and AN minus 1, such that rank A1 equals to R and rank AN minus 1 is equal to N minus R. Yeah, because then you can reconstruct A2 from A1 by our minor construction and so on. And also the late matrices you can reconstruct from AN minus 1 dually. normally. So in particular, we can also do the dimension count. And there is one more condition. So it's not true that arbitrary matrices with this rank belong to SR. So there needs to be a vanishing. So the image of A1 needs to be identified with the kernel of AN minus 1. Yeah. Okay. So in particular, if you want to parameterize a general point on SR, parameterize it. So what I'm describing right now will not be in bijection with points on SR, but it will be like a birational map. So a general point will write in an image. So first we look at a point in the Grassmannian GRN, and we think about this as this image of A1 or kernel of AN minus 1. And then we have to fix matrices with fix A1 of rank R with image equal to U, and fix A. Oh, sorry, this is not very well readable. This is A1 and this is AN minus 1 with kernel equal to U. Yeah, so if we make these three choices consecutively, notice that the second and the third choice become now independent, but they depend on this point on the Grassmannian. This is how we can parameterize general points of SR. And I encourage you to do the dimension count. Okay, so now we have our variety of complete quadrics, and if we project to A1, we get a map to PS2V, and if we project to AN minus 1, we get a map S2V dual. So these are nice maps, and they resolve this inversion, that map to A inverse. So notice that this is like a graph, but it's better than a graph because it's smooth. So it's not really the graph, although this maps pi1 and pi2 are birational. Yeah. So as long as the matrix, maybe I should call it pi n minus 1. As long as this matrix is invertible, you get a unique point QV over it, and you need a unique point in the image. It's only on lower codimension that these maps start to have different. Well, they are not well defined. Okay, so now we can change our problem. Namely, remember what we wanted to do is we wanted to have a subspace here L and the subspace here M. And we wanted to somehow see how many matrices in L get mapped to matrices in M. So these were linear subspaces of certain dimension, and these we can pull up to do intersection here. Why? Because these points, when we will be counting L and M, these will be invertible matrices. And on the set of invertible matrices, this pi1 and pi n minus 1, they are isomorphisms. So what I am trying to say is that phi nd is, yeah, so just as we were pulling back to graph, now we can pull back to CQV. So we take pi1, we pull back L, and then we intersect it with the pullback of M. These are general subspaces of yeah. So let me maybe write it. Dimension L is D minus 1, and dimension M is well, it will be easier to write codimension. It's D minus 1. Okay. So we want the cardinality of this intersection. Okay. Very good. So notice that this reduces. We can now do can now do computation in the chowering of the complete quadrics. And this is again, because this is a smooth variety. So, okay, we don't yet know what are these classes and so on and so on, but at least we reduced to something that is better. So now I will give you a few bad news. So I will not tell you what is the chowering of CQV. This is known, but not needed for those lectures and non-trivial. So our idea will be to still change it, to use slightly this ring, or at least a piece of it, so a degree 1 piece, so the Picard group of CQV. And then to reduce to something even simpler, Grassmannian, whose chowering we already understand very well. So there exists affine stratifications of CQV, and all this in principle would be possible on CQV, but it would be technically so difficult that it's better not to do it. Okay, so notice that we already have divisors. SR, or their classes. I will abuse the notation and I will say that this lives in the chowering. And in fact, it lives in the Picard group because it's a divisor. But we also have these projections, PI, to projective spaces of S to wedge IV. So in particular, if we take a hyperplane here, we have divisors that we will call Li, and by definition, this will be the pullback of a hyperplane. Okay, and in principle, it's completely not clear what these divisors have to do with those divisors. Well, even on very simple examples that we already saw on previous lecture, they don't have to be equal. Yeah, so one is rank something matrices, the other is a pullback of hyperplanes. So this is amazing. Like 150 years ago, although Schubert was not familiar with a lot of the language we have currently, but he basically proved the following, that L1 up to Ln minus 1, so the pullbacks of the hyperplanes, they form a basis. Of the Picard group. Okay. So it's very easy. And further, so if it's a basis, we have to be able to express any other divisor. So Si is equal to minus Li minus 1 plus 2 Li minus Li plus 1, where we are using the convention that if you are outside of the script, then you say 0. So where L0 equals Ln equals 0 by convention. Okay, so I give references for that, but let us just believe. And an exercise for you, one of the exercises that I suggest is to now express Li's in terms of Si's. That's not so difficult. I mean, you just have to change. If you work over Q, you just have to change one basis to another. So what have we actually proved? So notice that here, when we are pulling back L, we could as well pull back a hyperplane intersected with a pullback of a hyperplane intersected with a pullback of a hyperplane, because L is really, well, it will be easier for M because it has codimension d minus 1. So this is H to d minus 1. Yeah, and this is H to like the dimension of the space minus d minus 1. I will be off by 1 if I write it. Yeah, so these are different H's. One H lives here, and let me call it like H prime that lives here, and I will put a prime here, a hyperplane. So both L and M are intersections of hyperplanes. So for this reason, when we want to compute phi and d, what we really have to do is like, well, so we have to pull back hyperplanes. A pullback of one hyperplane is L1 by definition. And then we have to do it, now I will be precise with the dimensions. This is this minus d. So minus one's cancelled because from the one hand side we have a dimension of the projective space, but from the other we have d minus 1. And then we have times L n minus 1 to d minus 1. And well, then we have to write on what we mean this. So this is, we want the degree, so this is on CQ n. Now, if you do the exercise, you will know how to express L1 in terms of SIs, and I will here already give you an answer. So there is 1 over n. Well, we are still over CQ, and then we still one from here, so we subtract 1. We don't do anything to Ln minus 1, and then we have to express this L1. Part of it is already here, and the other part is a sum from s equal 1 to n minus 1, s n minus s. Okay. So this large S is the divisor we were describing at the beginning. Okay, so what now? Well, now we can go with summation out. That's the first thing we can do. So this is 1 over n summation from s equal 1 to n minus 1. And over the variety of complete quadrics, we have L1 to n plus 1 over 2 minus d minus 1, Ln minus 1 d minus 1. S goes out. I want S to go out. And then we have S and minus S. Okay, so this number we are after turns out to be closely related to the sum with some coefficients, rational coefficients of those numbers. So surprisingly, it's easier to work with those numbers. Oh, now I see that maybe my integral looks very much like S, so I will, this is integral, this is integral, this is integral. And everything else that looks like an integral is an S. Okay, so these numbers, these final numbers, magically will turn out to be easier to compute. So they deserve a separate definition. We define delta m n r. So this depends on 3 numbers, and by definition, this is CQ. Well, n I will write here to say how this depends on n, and then there is SR, L1 to n plus 1 choose 2 minus m minus 1, Ln minus 1 to m minus 1, and now comes also, I think each time you are doing intersection theory with a divisor, you could also pass to that divisor. So you can say that this is really intersection on SR. Yeah. So if you are intersecting A, B, and C, you can say that you are intersecting B and C on A. So here we will get L1 to n plus 1 choose 2 minus m minus 1 Ln minus 1 m minus 1. Okay, now using this definition, our formula for ML degree, so a corollary, this is a corollary from this proposition. We just have to replace those numbers by deltas, and what we get is that phi n d is equal to 1 over n sum from s equal 1 to n minus 1 s delta d n n minus s. Okay, you can check. This is very straightforward. Now, let me just say that the numbers delta that we have just defined, they also appear in applied mathematics, and they even have a name. They are not defined as I have defined them here. They are defined slightly differently, but we will get to that, because in order to compute them, we will have to slightly change our point of view on them. But their name is the algebraic degree of semi-definite programming. And the branch of mathematics where they appear is when you are trying to find an optimal solution. So let's say you are trying to maximize a linear function over a spectrahedron. A spectrahedron is a linear cut of the cone of positive semi-definite matrices. So it's a generalization of a polyhedron, and you want to maximize a linear function over that. A solution is some vector with coordinates, and you would like to understand how complicated are those coordinates. So a similar question as in algebraic statistics, you try to somehow, for example, find the degree of the algebraic extension where this coordinates lives, and this is exactly governed by those deltas, hence the name algebraic degree of semi-definite programming. A very, very interesting topic, slightly outside of the scope. There is also a purely algebraic geometry definition that does not refer to intersection theory. That's also funny. So imagine the locus of rank at most R symmetric n by n matrices, and intersect this locus with a general projective M-plane. That's a variety that lives in that M-plane. You can take a dual variety to that and ask for the degree of that variety. So notice, rank at most R n by n matrices intersected with an M-plane, and that degree is exactly delta MNR. Okay, so a very interesting number appearing in many contexts, and our aim is to now understand it better in terms of something that we actually can compute. Okay, so the trick is, so remember, before I told you that this is too easy. We need to replace it with CQV, yeah. And then we did something and we got SR, and I'm telling you SR is too difficult. We need to replace it with something else. So again, there will be a birational map, and we will change the intersection problem that makes perfect sense on SR. In principle, we could do all our intersection problem on SR, but that's complicated. And we want something simpler that is birational to SR, so that we can still look at our divisors LL and LN minus 1. We can map them here and do this, and we will do this intersection problem on that variety. And what is this question mark? We almost got it. So we want something birational. So we want something that looks almost the same on SR, maybe on a locus of higher codimension, it doesn't agree. So notice that we had a parametrization of SR that worked generically. So we started from the Grassmannian GRV, and we said that over a point on this Grassmannian, we need to choose two things. So if we fix a W here, well, we need to choose a matrix that has an image W. Yeah. So what does it mean? What does it mean? A symmetric matrix that has image in W. So if you look at your symmetric matrix as a map from V to V dual, and sorry, so let's say from V dual to V. As a map from V dual to V, and we would like the image to be contained in W. Now, a linear algebra exercise for you is that this map descends to a map from V dual to V, a symmetric one. And it's, if your image is in W, it's, I will write it with a tilde, but it determines A1 and is determined by A1. So choosing A1, a symmetric matrix whose as a map has image in W, is the same as choosing a symmetric matrix on W, so as a map from W dual to a W. But this, we know what parameterizes those things. Well, this is S2, W. So in other words, what we have to do is we need to choose a point in the second symmetric power of the universal bundle on the Grassmannian. That's A1. And for an minus 1, what we need to choose is the exactly dual thing. So it's a point here in S2Q dual. Okay, so altogether we need to, over each W, we need to choose a point here and a point here. So this is called the fiber product. It's a variety, and typically it's denoted as follows: PS2U times over the Grassmannian GRV PS2Q, and because this is a lot of writing, I will just denote it by X. Okay, so I claim that the question mark is equal to X. Why? Because a point of X, well, it's a point of a space on a Grassmannian, a general point of X, and it's a symmetric matrix with image in W, and then it's a symmetric matrix which has kernel W, and this is precisely what we want for SR, a general point on SR. Okay, so our aim, we started here. There was a base locus. We went here. Here we did some translation. There was no base locus on SR, but now we go back to X, and this is really going back from the construction point of view, because notice that over W, well, I basically already told you that if you fix this point in W, then how does SR look like? Well, it's a variety actually of complete quadrics, but on space W, and times the variety of complete quadrics on the space V divided by W. And now you replace those two varieties of complete quadrics back by the birational thing, by the projective space. So just quadrics on W and quadrics on the quotient. But the good news is that there is no base locus. So because you are doing this locally, and because you did some tricks passing from here to here, L1 and Ln-1 will have no base locus. Okay, so now what? So now our aim is to understand, well, Li and Ln-1 go to on X. And why is this easier? Because we have a very good description of what is X. Okay, so lemma. Yes, let me maybe redraw this diagram in the lemma. So we have our X that maps through pi1 to S2U projectivization, which maps, let's say, to pi2 to PS2Q dual, and they both map to the Grassmannian GRV by the maps I1 and I2. I1 is here, I2 is here. So what's delta MNR? Well, we need to ask ourselves, what is the divisor L1 on X? Well, a divisor L1, so I will finish this lemma in a second. Before that, we need to answer what is L1. So a divisor L1, how do we obtain it? Well, this is a hyperplane. In PS2V, okay? But this PS2V, I can regard it as a trivial vector bundle over the Grassmannian GRV. So as a projective bundle, yeah. So hyperplane, so corresponds to O of 1. Yeah, the class of O of 1 is the class of a hyperplane. Okay, now as a bundle, this contains P S2U. Okay, And O of 1 restricts just to O of 1 on this PS2U. Yeah? For example, maybe it's easier to see that O of minus 1 restricts to O of minus 1, because taking a point corresponding to a point in the projective space, it doesn't matter if you pass to a projective subspace or not. So L1 here on this space also corresponds to O of 1. Okay, so what we really need to do is we need to take the Chern class, the divisor, corresponding to O of 1 on the, I will write U, but I really mean S to U. Okay, so on this thing corresponding to S to U, and we need to take it to the power n plus 1 divided by 2 minus m minus 1. M minus 1. Okay, so this lives here, and this gives us L1 here, and now we need to pull it back to X. Okay, so this expression I wrote so far, it simply corresponds to this part. Okay, and now I have to still write this part. So this is what I will be doing right now. Well, first we have to understand what is our thing on this space, and this is similarly, this is C1 O of 1, but now on, well, I write Q dual, so very formally it should be S2Q dual to the power m minus 1, and now we need to pull it back. Okay, I know this is slightly fast. Think about it very well, how this loci of points are cut out, why this is O of 1, and so on. This is pi 2. Okay, and formally we should push forward this to a point to get a number, yeah, because this is currently a class on X, and to get a number we should push it to a point. But before we push to a point, we can push through something. And the good thing, so I will add something here, is to first push to the Grassmannian. So we first push through pi 1 and then push through I1. We could also do this with 2 over 2. And then formally we should push to a point, but this maybe I will not write for simplicity. It will be enough to push to the Grassmannian, because on the Grassmannian we already know how to count points. We just have to count the coefficient of the rectangle k times n minus k Young diagram. Okay, so now we go forward, and now I have to give you two general lemmas. They are very often used in intersection theory. And they work in full generality. So once, if you have the fiber product diagram, so just as we have, so if we have X mapping to Y mapping to Z mapping to W, and here we will have F2G2, F1G1. Well, in order for the pullbacks and push forwards to be well defined, let me just assume, well, actually it's enough to assume that F1 is proper. Okay, let me just check if I did it. So from X to Y we have F2. Sorry, this from Y to W, for some strange reason I denoted it by G1. Oh, sorry for this. But I want to be the same as in the notes. And here I have F1. Okay, so now it's easier to write, because if F1 is proper, then F2 is proper. So we'll have F1, F2 proper, and G1, G2 flat. So these are our assumptions. Then we can change the order in which we are doing pullback. So we start from Z, and we first do the pullback and then push forward. And this is the same as first doing the push forward and then doing the pullback. So these are the maps from the chowering of Z to the chowering of Y. Okay, so this is the first lemma. And the second lemma, is as follows. So if we have f from y to x proper, then if you take a push forward of intersection of something from x with y, then you can somehow cancel the push forwards and pullbacks. So it's like this, where for all x in a x and y in a y. Okay. Okay, so with these two lemmas, armed with these two lemmas, we can start computing our diagram. So okay, maybe I will redraw it. We had pi1, pi2, and we had I1, I2, I1, I2, and our aim was to compute the following. So we pushed forward as follows, and here is the important thing. This is the thing responsible for A1, O of 1, well, it's on U, or on S to U, to n plus 1 choose 2 minus m minus 1. And this thing we need to intersect with pi 2 inverse, and now we have C1 O of 1 on Q, or S2Q, Q dual, yeah, S2Q dual, m minus 1. Okay, so notice that, well, I could also put brackets like that. And now we have push forward of a pullback with something. So we use the lemma, and these two cancel. And what we are getting is C1O1U to n plus 1 choose 2 minus m minus 1 times, and now we have pi 1 push forward, pi 2 pull back of C1O1Q dual m plus 1. Okay, now notice what have we got here. We have going up and down, so this is the same as going down and up. So we can change it to first pushing forward with I2 and then pulling back with I1. Okay, so I change this box into this box. But now notice that I have a push forward of something times, well, a pullback through I1. So again, I can use the second lemma. So here to change the boxes, I use the first lemma. Now I use the second lemma, and I get I1 push forward C1 OU1 n plus 1 2 minus m minus 1, and those cancel, so I get I2 push forward C1 O1Q dual 2 power m minus 1. It's supposed to be minus m minus 1. Okay, but this looks something that we know from a definition. This is a definition of a Segre class of a vector bundle. Yeah, push forward of C1 of O1 on the vector bundle. And this is the Segre class of S2Q dual. So the corollary of all this is as follows. So Segre classes needed some restrictions, and I will just write them now. So a corollary is as follows. So if we have n minus r plus 1 choose 2 less or equal than m, less or equal than n plus 1 choose 2 minus r plus 1 choose 2. And it's very good to understand those inequalities. They basically assure us that our number that we are computing makes sense. So maybe before I go further, let me just say a few words on this. So notice that we were intersecting those hyperplanes in this PS2U and those hyperplanes in PS2Q. Now, if you take a lot of hyperplanes here, you can cut to zeros. And if you take a lot of hyperplanes here, you will also obtain 0. So, and you know, the number of hyperplanes you take in the one part, the more you take in one part, the less you take in the other part. And there is this sweet spot, which is exactly given for those equalities, where you don't get zeros on both sides. Okay. And this is exactly, these are exactly those inequalities. These are known as Pataki inequalities. Yeah. Please make sure that certain push forwards will be zeros when you are outside of those inequalities. So if this holds, then delta m n r. This is just well, again. So now I will write that I push forward from the Grassmannian. I didn't write it in my computations, but now comes this integral, and now I have to take the Segre class. Which Segre class? Well, this is n plus 1 choose 2 minus m minus r plus 1 choose 2, because there is, you remember, this shift in the Segre class and the exponent coming from the rank of the bundle. And now, well, this is the S2U. I will write it formally. I will not just write U, because that would be very confusing. So in all those computations, I should really put the very small S2U. I don't want this because it's already hard to read. And every Q dual should be S2Q dual. And this I have to multiply by the Segre class M minus N minus R plus 1 choose 2 of S2Q dual. Okay, notice, so this is times and this is just the end dot. Okay, so notice that we basically reduce to something very straightforward. If we manage to understand those Segre classes, this will be basically a game on Young diagrams to compute those numbers, a combinatorial game. And this will be our main point of attack during the last lecture. I should also say that otherwise, and you can consider it as an exercise to prove it, delta m and r is equal to 0. So if you take too many hyperplanes on one side or another. Thank you very much.